And our next speaker is Tim Miller from NET, Neuro Electronic Technology.
Hello.
He will talk about ready to integrate a smart vision solution for your embedded vision system. Mr. Miller, please. Auf den geht's weiter.
Good afternoon. My name is Tim Miller, and I'm responsible for the product management at NET. Today, we introduce you how you can use smart vision technology to create your embedded system. The NET is part of the TKH group, which is listed on the stock exchange with an annual turnover from 1.5 billion euro. The TKH Vision Group consists of 8 companies who are happy to welcome you at our joint booth here at the Vision Show. Especially in the medical field, NET can look back on 25 years of experience in embedded vision systems. We can proudly say that our camera systems make the work of the physicians easier, safer, and more accurate in many operating rooms around the world. And we reduce the stress of an operation for the patient by using the smallest image sensors with an image enhancement algorithm by NET. Since the start of our latest Gigi Vision camera in 2013, which already allows customer-specific pre-processing, we mainly offer our smart camera systems to our customers. In addition to our core business of camera technology, NET has a strong expertise in optical components. We design and calculate optical systems for the special applications of our customer, but we also have over 1,000 different standard optics, such as telecentric lenses in our portfolio. The requirements of an embedded system are and always have been very high. In addition to the poor functionality and processing power, the various applications also have very different requirements. Embedded vision systems consist of many different components. Each of the squares represents a property of the component. The difficulty is to get the best possible performance out of this multitude of different components with different individual properties. The performance of an embedded system depends very much on how well the individual components work together. Selecting the right sensors, you can fall back on a large number of technical features such as resolution, frame rate, or spectral sensitivity. Some of the interfaces are standard, like the USB 3 Vision or the well-known Gigi Vision. And even these standards cannot simply be exchanged. The sensors have interfaces such as MIPI or LVDS, and every manufacturer has its own particularities in interpreting the standard. The heart of an embedded system is the CPU, which of course influences the selection of an operating system. There are different operating systems such as Windows, Linux, iOS or Android that have to match the software you want to use. If we put these variables together, there are combinations that fit optimally. In this case, we see that the combination of an Intel CPU fits perfectly with the Windows operating system. An ARM processor as a CPU would be a very unusual combination right now. Some combinations fit with restrictions, and in the worst case, some of them can only be brought together with a great effort. Here we see the requirement to use an Android system. The combination of an ARM with an DSP is less flexible. An ARM and an FPGA combination would have been the better and more flexible choice here. In addition to the main components, many others have significant influence on the success of an embedded system. In order to communicate with the machine controls or to implement an HMI, interfaces are necessary. Starting with optics, cables, lighting, interfaces for the machine control, mechanical conditions, additional measuring devices, software tools to use hardware acceleration, image processing software, and customer applications with an integrated HMI. All of these components are part of the overall image processing system. Our newest system, IM, fits to a wide range of applications as an embedded vision platform. IM allows decentralized image processing on an edge device. The flexibility in hardware and software opens up new possibilities to meet your requirements for an embedded system. A flexible lens mount with S-mount M12 size. C-mount is the most widely used mount, or even F-mount for bigger sensors or line scan sensors will be available soon. Right now, IM offers high-resolution image sensors from VGA to 12 megapixel or even higher. Rolling shutter or global shutter, visible, NER, up to SWIR sensors are available. Most of them are the popular IMX sensors, which are widely used in the visual market. Multi-sensor applications, up to 4 sensors are possible. For example, for stereo vision application with hardware acceleration on the FPGA. The housing with an industrial design takes care of an efficient temperature management. Board-level variants with a customizable individual cooling management are possible. The ultra-scale SoC contains a quad-core ARM CPU and an FPGA in one chip. Many of our vision tasks, or many of your vision tasks, can be hardware accelerated in the FPGA. For example, a neural network can be accelerated with a Xilinx Vitis DPU on the FPGA. The system is equipped with a GigaVision server and allows plug-and-play use like with any standard GigaVision camera. There are digital I/Os available for machine control, for example, to work with an incremental encoder. Our open embedded vision platform allows customers to access the FPGA and the ARM processor. With the Xilinx Vitis United Software Platform, you can use the resources of the FPGA without knowledge about hardware description language like VDHL or Verilog. It has never been so easy to use hardware acceleration. Besides in-house developed algorithms, standard software libraries from the market are also working on IM out of the box. Future interfaces, depending on customer requirements, are planned, like the Fightbus, the Profibus, CAN bus, or EtherCAT. Even a 5G or USB 3 interface is planned. IM is a completely engineered embedded vision system, ready to go. IM reduces your time and development effort in order to reach your goal for an embedded system. We can see very well how our standard camera on the left side becomes a customer-specific solution on the right side. The cooling concept was adapted to the mechanical conditions. The interface board has not been functionally changed, but has been adapted to the mechanical conditions. The LED control was added. The standard Ethernet connector became an M12 connector. The main board remains unchanged and was only rotated by 90 degrees. The sensor board remains the same. Only the connections are adapted to the rotated mainboard. The optical mount was unchanged. So a new customer-specific variant has been created that has an independent customer design. So if you look on the system overview, the image sensor is connected to the FPGA with LVDS or CSI2. These two options open up a very wide range of sensor selection for our customers. The sensor interface on the FPGA works with our SynView, that's our SDK and API. Through the API, the image data is provided to the ARM processor. The application can now access image processing libraries like OpenCV or even commercial libraries like Helken, Mill, or Zebra Aurora. For hardware acceleration, the user can use the resources of the FPGA by using the Xilinx Whitey's tools without knowledge of HDL. The output to a higher level system can take place via GigiVision. The system works like a GigiVision camera. Here we see an example of a hardware acceleration for the OpenCV filters onto the FPGA. That example we also provide online in the GitHub, and you also can see it here at our booth in Hall 10. In example 1, various OpenCV filters consisting of color transformation, blurring, thresholding, and edge detection, also reg informers, are processed sequentially on the ARM processor. In example 2, the filters are pushed onto the FPGA by using the Xilinx Whitey's United software platform. There, they are processed in parallel and require significantly shorter process time. The DPU, the Digital Processing Unit, here is used for an acceleration of a neural network. The various networks consist of reference images. These reference images, which must be available in a large quantity, are used to train the network. These networks are trained with a training framework such as TensorFlow, Keras, Caffe, PyTorch, and so weiter, and so on. The next step is the optimization in order to perform optimally on the SoC, on the FPGA. For this purpose, Xilinx offers the toolset Whitey's AI as a Docker image. The network was calculated in floating point arithmetics and is quantized and converted to work with the hardware accelerator. A so-called DPU is already installed on the camera on the FPGA. We call this IM machine learning ready. The optimized and quantized network is processed faster on the camera by the DPU. This means that even compute-intensive applications can be executed on the edge device on the embedded system. In this example, we show you a project with segmentation. Various natural shapes, such as trees, grass, animals, or the sky, are taken into account to use a trainer or train a neural network. The network is trained with the TensorFlow framework. With the Whitey's United software platform, the trained neural network will be prepared for accelerated use on the hardware, called DPU. The trained network is uploaded to the vision system for processing. The embedded vision system, IM machine learning ready, is already equipped by NET with optimized hardware acceleration, the DPU on the FPGA. Customers who want to transfer their own neural networks only need to transform them in an automatic process. The position of the objects in the image can be determined through segmentation. In this case, an agriculture machine can become autonomous. It can also be distinguished between reaps and crops and control various tools such as a cutting device. Beside the hardware acceleration, the vision system takes over the complete application control. In the last 15 minutes, we showed you how you can benefit from a ready-made smart vision solution and still remain flexible. You can find detailed information about our IM embedded platform in our video tutorials on our website. With our quick start guide, we will show you how you can take the first steps. We will also show you how you can use your own software or integrated vision libraries. We show you how to use open source tools and what possibilities the Xilinx Whitey's United software platform offers. We show you how you can accelerate a neural network for the IM smart camera. With our open camera concept, you can also use the resources on the FPGA. And we remember, you do not need any HDL, hardware description language, to program or design knowledge for that. So we look forward to meet you personally here at the Vision Show on our stand at the TKH Vision. And thank you for your attention.
Thank you for the lecture. Okay, there are again no questions. And so we have finished this session. Yes, and very early. Maybe it's the daily record for now. And you have a short break. The next session is about camera technology. It will start at 2 p.m. Yeah, have a nice day and goodbye.